known for its marine layer and its fog, and sometimes it can block the view a little bit. Okay, let's get started with the questions. We've got the media on the line. Make sure you mention the individual to whom the question is directed, and we'll start with Bill Harwood with CBS News. Bill? All right, we are having some audio issues there. We'll get those resolved. In the meantime, let's take some social media questions. And we've got some good ones here. The first one is, how long have you been working on DART, and what has been the most challenging aspect of this mission? Ed, why don't you take that one?
The Applied Physics Lab has been working on it for well over, from just the basic idea. It's been at least 5 years, but from cocktail napkin to going through just the early idea development. I myself have been with DART for about 2.5 years through the build of the spacecraft.
All right, very good. How about another question? Is there any chance DART could send Dimorphous, this is the asteroid in which it's going to make impact with, into a new path that could threaten Earth? Are there any other potential unintended consequences? Dr. Zurbuchen, why don't you take that?
The short answer is no. We know this dimorphous is sitting at a gravitational well of Didymos, right? And so you can calculate how much kinetic energy we're bringing, and you just do it's quite a simple calculation you can do, and just convince yourself, no, it's not possible for it to be pushed in any fashion in a way that it will be a concern for us. We're not aware of any unintended consequences relative to the object, relative to the Earth. I have to tell you, I'm really looking forward to actually learning what happens during such an impact. How many rocks will come off the front end, for example? Considering, we look at Bennu, we look at other images, these asteroids sometimes look like gravel pits, right? So an interaction of a spacecraft like this with a gravel pit, how will it go, right? So for us, there are certain ideas we have. I'm sure, as always, when we actually do this, we're going to learn a lot. But one of them that I'm sure will not occur is that there will come a threat to the Earth as a result of it.
All right, thank you very much. And so we've got our phone bridge back up and media questions ready to go. So let's have Paul Brinkman with UPI ask his question. Paul?
UPI, can you hear me?
You can indeed.
All right. So I guess this is for Ed. Perhaps I should have asked this earlier in the preparations for this launch, but I find myself wondering how unique is the structure of the DART spacecraft? As someone said earlier, NASA doesn't typically launch missions just to crash them. So was this spacecraft designed structurally for such an impact? Or, does it have a rebar frame in it or something, or a ramming device at the front of it? Or is it simply the mass, was it simply designed for the trip through space? Yeah, I guess that's it. Thanks.
Okay. The easy answer is it's designed and built just as we build other spacecraft. It's we tend to use a lot of aluminum and honeycomb aluminum to build decking structures, but there's nothing special. There's no ramming device that we've put in the spacecraft. The technique is basically the mass of the spacecraft itself, and you hit the asteroid with that mass, you will have a reaction.
All right, very good. Our next question is coming from Chris Davenport with the Washington Post. Go ahead, Chris.
Thanks so much. This is for Dr. Zurbuchen. Asking you to maybe take a step back, because so much of the focus this year has been on human spaceflight with commercial crew and Artemis, etc. But obviously it's been a big year for science as well. And I was just hoping if you could just take a moment to reflect on that and place the DART mission in this broader context of some of the other missions which you mentioned in your opening statement. I'm just sort of curious which stand out to you. What are the highlights? Thanks so much.
Well, I really appreciate the question. First of all, I'm super excited about all the successes on the human spaceflight side. We at Science are huge champions for that, and we sit there glued to the TV just the same way as everybody else, when we see these astronauts going to space from American soil, and we're just so excited about this whole thing. This has been a year of science, though, in an amazing fashion. Of course, that this year alone, we landed on Mars. I still remembered how I felt, especially the night before, worrying about everything that could go wrong. We, of course, took the first flight, kind of our Wright brothers moment in an extraterrestrial fashion with the Ingenuity helicopter. We just announced minutes ago that flight number 16 was also successful. I want to remind you that this vehicle was built for 4 flights, and so we're exceeding in leaps and bounds. You remember, of course, and you already mentioned that we put Landsat out into orbit to extend this 30-year of record of the Earth, kind of one of the most important data sets that are there, economically speaking, besides GPS, the second most important in terms of even the economic value of it, but scientifically, just a treasure trove, right? You talked about Lucy, that is there. We already talked about it, exploring the Trojans and IXPE, this X-ray polarimeter that will launch in early December, is a small explorer, and it's mighty in its own way, built by NASA Marshall. It's a mission that will look at the sky, especially the violent sky, the black holes, kind of exploding stars and kind of weird objects that are really hard to imagine, like these pulsars. We'll look at it in a new way. And of course, at the end of this year, towards the end of December, of course, we're ready to launch Webb, which is a telescope that has been 20 plus years in the making, and we're ready to get it up there. Besides all of that, we've had some amazing science breakthrough. The InSight papers that came out, I've kept count of multiple journals, Science, Nature, that had, in fact, science results at the title page from NASA, including the most recent one in Science, which has Juno results of Jupiter. So we've had an amazing year, and I want to tell you, next year is just going to be the same way. We're aware of 10 launches next year that we want to do, some of them with new launch vehicles that are there we haven't used in the Science Mission Directorate. But yeah, it has been a year of science, and the next year promises to be the same way.
All right, let's go back to social media now, and 11-year-old Hayden wants to know. First of all, he has a statement. I want to wish you all well. I'm excited for this launch and for the future as a planetary defender. How excited are you all for those first images of Dimorphos and Didymos up close? Lindley, why don't you take that?
Sure. Well, thanks for your wishes, Hayden, and thanks for joining us as a planetary defender. Well, it will be quite exciting in the last terminal approach of DART because we don't see the moonlit Dimorphos until the last hour of the mission. The DART spacecraft will pick up the larger asteroid, Didymos, a few days to weeks before the impact, but we actually won't see the moon until about an hour before we have to impact it. So that's going to be an exciting part of the mission to see it, gauge exactly where it is, what its size is, and target in on it. So we expect excitement come the end of September as the mission team guides. Well, actually, the mission team guides to the to Didymos, but then the spacecraft has to find the moonlet and target itself.
Ed, you must be looking forward to those pictures as well, no?
Yeah, it's as Lindley said, you'll go from the point, just a little point for the longest time, and then it's in the last hours that you begin to resolve a moon, and then you're gonna see the smart nav start taking over, and it will pick the moon. It will start directing the spacecraft toward the moon. And so I think the excitement is from there's the imagery itself, which has scientific value, but then there's also the engineering of just watching the spacecraft do what it's supposed to do. And then it's going to be, we're streaming these pictures once per second, and each time we get a new picture, it's going to get better, and to the point that we're going to be right up, those last pictures are going to be right up against the asteroid, and then it's going to be complete silence. So it's going to be, there's going to be a joyfulness there, but there's also going to be just the sadness that the spacecraft is gone. But in the end, it did what it was supposed to do.
Yeah, kind of eerie when the communication from the spacecraft stopped suddenly, right?
Yes.
But certainly expected, and that is the mission. Let's get back to the media line now and see if we can get Bill Harwood with CBS News in here. Bill?
Hey, thanks very much. I appreciate that. Two quick ones. For Ed, is that the biggest challenge for DART? Is it the guidance and simply getting to your target and hitting it where you want to? I mean, if you get that far, you're obviously going to deflect the asteroid, and just how much it deflects, of course, will be scientifically valuable, but is the real challenge just getting there? And quickly for Dr. Z, you mentioned JWST. Could you give us maybe a little bit of an update as long as we're all here? There weren't a lot of details in the blog post this afternoon. Thanks.
All right, let's start with that.
Okay. So we've really looked, over the years, we've looked at making SmartNav as robust as possible, and we've looked at every different combination that we can think of in terms of how could the spacecraft be behaving, and then also even what is the shape of the asteroid. So right now we see the asteroid as just light curves where we point our good telescopes up at the system, and you just see a point of light that gets lighter and darker, and the scientists are able to glean. Part of that light is the rotation of the larger body. Part of that light is the moon orbiting around the larger body, and part of that light fluctuation is the rotation, the spinning of the smaller moon. And they're able to glean a lot, but we don't know what the shape is. So we've done a lot of simulation of spacecraft performance, sensor performance, and the dynamics, and the shapes of the moon. So we've got a really good confidence that that we will hit the asteroid. But we keep trying to make it more. As time goes by, we try to make it more and more robust. We've done everything we can on Earth with the spacecraft in our data collection and our analysis. At this point, the natural thing for us to do is to launch the spacecraft, get it in space, and then actually get real data on our sensors so that we can tell, instead of using some conservativeness in our modeling, we get real data in our modeling, and we use that into our simulations. But in the end, it's still it will only be in those the last hour that we get a good feel for what the shape of the moon actually looks like. So we really work hard to provide as much robustness in being able to hit the asteroid.
I guess I'm going to focus on web now, which is the question you asked. And of course, we put a little blog post out which has information in it, but let me use my own words for it. And a few days ago, as we were attaching the spacecraft to that connector that, of course, then will mate to the launch vehicle, that clamp band that was attached to it, that made together, it's a clamp band with very high tension. We had, in doing so, we had an anomaly. That clamp band came off, and kind of in a way that the clamp band is not designed to come off. Again, it was an anomaly. And of course, when you work on a $10 billion telescope, kind of conservatism is the order of the day. So what we have done, and frankly, many of you have, some of you have covered missions, others have worked on these missions. We always think about what could happen. We actually spent quite some time looking at the potential kind of energy that went into the spacecraft there. We expected that, based on kind of our experience levels, what of course had happened because we're so far down the stream, we're literally kind of there, finalized everything. We did not have the normal sensor that would the sensors that we would have on spacecraft, for example, that we had when we transported it, they were no longer on the spacecraft. And just for sheer caution, what we have done, after these calculations, is gone back to a small number of subsystems and just do the functional tests to just make sure that, with all that conservatism, with just to be sure that that nothing happened as this kind of energy went into the bus. So that's what we're working on. That's why we need just a few extra days. Again, we've always said that we will launch this telescope when we're absolutely ready to go, and that is just the right thing to do right now, is to do these tests to make sure that everything is as ready as we think they are. I hope that in just a few days here, we will be in good shape. We'll know that. Surely we'll keep you informed as we go forward with it.
All right. Thank you, Dr. Zurbuchen. And the next question comes from Stephen Clark from Spaceflight Now.
Thank you, Stephen Clark from Spaceflight Now. I think one of my questions is for Ed. Ed, if you could walk through what happens with the spacecraft after it comes off the launch vehicle in terms of when you get the first acquisition of signal, when do you deploy the solar arrays, and when do you activate the ion thruster system? And also, is the ion thruster system required to get to Didymos, or could you do those maneuvers with conventional propellants if necessary? And also, just to follow up on something Dr. Aziz said up front about a possible discount that SpaceX provided NASA, I was wondering if someone, Omar or Julianna, can talk about that, if that's true, and what kind of discount NASA got.
Can I just go first?
Yeah, sure.
I just want to make sure that I understood. This is, Swiss people or Swiss-born people should never make jokes, because frankly, they're really bad at it. What I tried to do is make a joke. I said we did not get a discount, I'm told, because of the fact that the fairing is so much bigger than the spacecraft. So no, there's no discount. Literally, we were making fun of each other. Our friends at SpaceX, at Launch Services, were really good friends, so we make fun of each other. So I put a joke over to Julianna. She may want to say something on her own, or Omar, but I just wanted to be sure that I take any and all kind of things out of the way that gave an opposite impression. Go ahead.
We got a pretty good price on the launch vehicle, though.
Okay, yeah. So to answer your question, let me start with a little going backwards also. So the next C thruster will begin, to answer the critical question is, we do not rely on the next C thruster to achieve mission success. We come off the rocket. SpaceX has put us on a ballistic trajectory that carries us on a direct path to the asteroid system, which is really beneficial in terms of we can do this entire mission with a hydrazine propulsion system with actually very small thrusters. They're the collection of thrusters that we have, they're all the same size, and they're all about 1 Newton, which is about a quarter pound of thrust per each of the thrusters. And so the next C thruster is one of our demonstration technologies. It's next C, the N in next is next, the next generation of ion propulsion thruster. And so we're using our 10-month cruise phase to really, we're going to be doing what's called neutral burns, in which we actually will put the spacecraft, we'll keep it on that ballistic trajectory, but we will put it into a corkscrew, trajectory in which the next C thrust will overall, when you integrate it, it will cancel itself out, and so there's no danger to mission success that next C will take us on a trajectory that's not on the ballistic path, and then have a failure, and then we would have to work to get back. We've planned this out very, very carefully. We will do a little bit of commissioning with NextC during our commissioning period, but it's really toward months 7 and 6, 7, and 8 that we will actually really do the exercise of next sea with those neutral burns. And so it's fairly late in our cruise trajectory that we really try to get, and our goal is to get 1,000 hours of demonstration time on the thruster just to prove its performance. And then the last question was basically, what's the timeline? And we're in an unusual trajectory where we will go south, and then we will. If you look at the trajectory, it's basically going over a portion of the South Pole before it starts to come back up. And in our first real, we will have a contact with New Norcia. That's about, I think, I'm guessing here a little bit, but it's about 40 to 50 minutes after launch. It's a good contact for receiving telemetry. It's not a great contact for commanding. So we actually hold off until we're over Madrid later to the point where we can actually have a good, robust command link, and that's when we start doing things like doing commanded functions. But from over New Norcia, that's when we begin the solar array deployments, and it will take us about an hour to deploy the solar arrays. And so that's the kind of the critical thing is launch, get into good ground station coverage, and then have the spacecraft will automatically start deploying the arrays on their own. But that's so that we get power positive as quick as possible.
All right, very good. Now let's take a quick social media question, because this one was a popular one on our Kennedy accounts. We're going to pull up a picture here that Dr. Zurbuchen showed at the beginning. And the question was, I saw this photo of DART inside the payload fairing, and I'm wondering, why is there so much extra room? Julianna, you want to take that?
Sure, I'd be happy to. So actually, to touch a little bit on both answering that question and the earlier question, one of the ways we can save launch costs is to have a common configuration. And so for our vehicles, even though we have, the spacecraft of varying sizes, including the smallest and the largest, by flying a common fairing size, we, have a single configuration that we can pass on the cost savings to the customer. I think so DART is actually going to a really high energy orbit, and so that's why we actually have to land the booster downrange, because it's going outside of Earth's orbit, so we're using all of the energy on the rocket to deploy it beyond Earth's orbit. One other note I think it's important is reusability is really key for lowering the cost of launch. The DART mission and the XB mission, both coming up for the NASA Launch Services Program, both use flight-proven boosters, and it's with reusability that we can enable low-cost access to space. That's important and enabling for even more science for us. So that's something we're really excited about at SpaceX, and we're really excited to partner with NASA about.
All right, thank you, Julianna. And now let's go back to the media line and get a question from David Curley with Discovery Channel. David.
It's a figure call. A couple things. It could be DART or APL. Do you have a place in the asteroid that you'd like to hit, or you just want to hit it? You're really not targeting any specific part. And Dr. Z will come to you for a stand-up in saying it, but seriously, this is formulas and equations, and whether you're betting that or not. If DART hits the asteroid as expected, what do you say the odds are that the orbit has actually changed? Thank you.
If you hit the asteroid as expected, how will you know that the orbit has changed, I believe, Ed?
Okay. All right. So when the algorithm is designed to hit the center of the moon, and so, but we did look, when we first started looking at the problem, we were really trying to hit within the center 15 meters of the moon, and that was. But the more we looked at it and did our simulations, we came to discover that, if we hit the asteroid, period, just the dynamics involved will achieve the requirement that we change the asteroid by at least 73 seconds in its orbit period. We believe, and our simulations are showing much better than that. But we're looking to, if we hit the asteroid, we're looking to change that orbit period by about 10 minutes. Can you repeat the second part of the question?
That was the second part. I believe it was difficult to hear the first part. So, David Curley, if you're still on the line, can you ask the first part of your question again?
That was actually the first part. The second part was Dr. Z. The question is, are you a betting man? And if it hits it as expected, what do you think the odds are that it actually changes its orbit?
What are the odds that it will change the orbit if it hits it as expected? He's a little choppy.
So the odds are 100% that if it hits it directly, it's 100% that it will change the orbit. It's very hard to imagine a scenario in which you come with a lot of momentum into a body like this, create an interaction, and kind of nothing happens on the other side. That's very hard to imagine. I think the thing that's hard to think about is, this system, these double asteroid system, rotates at about 12 hours rotation speed. So it's a very, very, very slow rotator, which is another reason why imparting that momentum will be very much measurable. So if we hit it, odds are 100%, I would say, to the best of my knowledge and thinking about this, frankly, many times, are 100% that it's measurable.
All right, very good.
Could I add to this just a little bit? Yeah, sure. Yeah,
Yep.
And how we know how much we've changed the orbit, how we know we've really changed it, is then Earth-based observatories will observe the eclipsing binary and see the change in the period of the eclipse in the orbit. So that's how we tell how much we've changed it by.
Ground-based telescopes, absolutely. Thank you for that. So we'll try to make these answers shorter so we can get through the rest of the questions. Question for Omar that came in on social. Why was this trajectory chosen for DART?
The trajectory is simple. From a physics point of view, it's a direct trajectory ascent. You could have done it probably from the Cape also with the kind of energy that we have with the Falcon 9. But yeah, it's a simple point and shoot.
All right. Very
sort
good.
of.
Yeah. Good, great answer. Back to the media line. Chelsea from space.com. Go ahead.
Hi. My question is likely for Dr. Z. I'm curious, this is essentially a practice round for what if. So how close to Earth or how close would its trajectory have to be, and how big would an asteroid have to be for NASA to consider using kinetic impact technology like this? And would that actual operational craft be quite similar to DART, or would you expect it to be bigger, meatier? I'm curious.
Yeah, I think those are perfect questions to ask. And the way I think about it, frankly, as I mentioned before, at this moment in time, we don't have a single object that really is a threat to Earth. One could imagine a number of scenarios, and I'm really interested to see how we're going to take that technology and move forward. Like, I could imagine, for example, that we have a series of such impactors, a small number that are actually in orbit, and ready to go in case a threat occurred. I could also imagine if we have a specific object that we would discover, during the NEO surveyor that Lindley talked about, or otherwise, that, we would create a mission specifically for that. The mass and the encounter kind of trajectory would strongly depend on really the incoming trajectory and the threat level that is there. So I think if you want, there's almost too many variables to give a concise answer. So there's a number of thoughts of the type that are there. Lindley may want to actually add something if he wants to.
There are a number of scenarios: the orbit the asteroid's in, the size of the asteroid. But the real answer to how far away do we want to intercept an asteroid is as far away from Earth as possible. And so our objective is to find these objects as far away in time and as far away from Earth and be able to enact this change in their orbit many years in advance, so it doesn't take much energy to change them at all. And then what would have been an impact down the road, it becomes a complete mess of the Earth.
All right, another question from Jeff Faust at Space News.
Hi, quick question for Omar. You mentioned that this is the first LSP mission to use a previously flown booster. What sort of special analysis did you need to do given the agency's experience with previously flown boosters from the commercial cargo and commercial crew programs? Thanks.
Right. So our engineers had to go through a rigorous process of certifying the reuse of this vehicle for this type of mission, for all our missions actually that are flying on the Falcon 9, and they came through the study of seeing what was being done, the flight history of these boosters, and certain limitations on parts and selections. The team did come up with a cohesive strategy, and we're able to use that. So yes, it's been a rigorous look, not only from us but the other government users also, to be able to certify this vehicle for use other than first times.
All right, very good. And last question that we'll take is from Marcia Smith with Space Policy Online.
Thanks so much. My question is for Ed. And I'm curious, you've talked a lot about SmartNav and you've talked a lot about the propulsion systems, but I'm not clear if the impossible happens and SmartNav is off and you miss, can your propulsion systems bring you back around for a second try, or is this just one shot on goal?
We work really hard not to miss. So we've looked at our sensors, we've looked at their limitations. We've actually made changes to the spacecraft during development and test when we found out that we could improve the likelihood of impact, probability of impact. We're doing things like better, pointing the star tracker more aligned with the imaging sensor Draco. And so we keep working harder and harder to not miss, but there are limitations to the sensor technologies. We do have, when we impact, we're launching with 50 kilograms of xenon for that ion propulsion system. With the demonstration, we'll use, with demonstration of the next C thruster, we'll use about 5. So there's still 45 kilograms of xenon on board the spacecraft that could be used as a propulsion to retarget. But right now, we're not keeping a list of backup dual asteroids to retarget against, but the possibility is there.
All right, very good. And that last question will do it for today. I want to thank all of my guests for joining us and providing us the great information and answers to keep us all informed about what is a really exciting mission that's going to end in the fall of 2022 with that impact into the asteroid around the September-October timeframe. But first, we got a